So we are going to introduce our next speaker. So Professor Shan, who was at the University of Chicago, will be giving her talk on improving the correctness, performance, and energy efficiency of machine learning applications. So let's give her a minute to get set up.
You have the presentation on? Yeah, do you guys have the presentation? Okay, start presentation.
Okay, so I'm very happy to have this opportunity here to share some of the research that we have been doing. And before I start, because I've heard many amazing talks, so I want to first admit that I'm not doing machine learning research. I'm not expert in machine learning at all. So of course I have collaborators who does machine learning. So my main research area is about finding bugs in software, or just and these bugs mean not just buffer overflow, bugs that cause your result to be incorrect, also bugs that cause your software to be inefficient, okay, and has performance problems. So that actually was the theme of my research. So of course I'm fascinated by machine learning because I feel like in the future I expect that most software will contain some machine learning component. And as a result, right, how to make sure that you use machine learning in a correct and efficient way will be very important. Okay, so I don't need to motivate you, right? So machine learning provide very effective solutions. But now if we think about the software that use machine learning, right? What will be a successful, right, application, machine learning application? So I think we need to consider correctness, right? And this correctness is, of course, we understand that, right, a machine learning model, right, we cannot guarantee, right, that they offer 100% correctness, but at least I hope the resulting software, right, that will be correct most of the cases. And also we need to make sure that the performance, right, because we are talking about big model, right, and the big model takes time to compute. So there need to be a performance consideration. And finally, no matter the machine learning model is deployed in the data center, right, in supercomputer or in our edge device, there is an energy consideration there. And this actually is not easy at all. So just an example, if we're going to deploy, right, the software running inside the device, then we need to consider how to pick the model, how to do local resource scheduling, and we need to think about how to write the software. And I'm saying it's not easy because think about how to pick the right neural network, right? I know we have been, talking about, right, we want a big model. But if you really deploy in an edge device, right, then you need to consider that, yes, you have big model, very accurate, but take a long time to execute, right? And then on the other hand, if you have, imagine you have a streaming data and you want to process the streaming data in a timely manner, right? So then you may think, hey, should I just pick the simplest model, right? So that I can always finish on time, but of course the accuracy would suffer. So you may want to consider, okay, let me look at what kind of application this is, right? Is there a deadline for my model's inference? And then maybe I want to pick the one that can finish right before the deadline. Well, that's still not the answer because there's a runtime environment, right? If it's not running in a data center, I cannot make sure that, oh, this machine learning thing is the only thing that is running on my computer. So as a result, because of the runtime, the interference from your environment, right? So it's possible that I expected to finish before the deadline, but because of extra resource contention, right, I may finish after the deadline. Then you get no answer at the moment of the deadline. Or another situation, right? Turns out my other tasks on this CPU are all sleeping for whatever reason, so I finish ahead of time, right? Then it will look like I've wasted some time. I could have used a bigger model to get a more accurate result. So that's a challenge if you really think about deployment. And then of course, in a device, right, in a consumer device, you also need to think about how do I do the scheduling, how do I set the frequency of the CPU, and all kinds of things. And there are tons of problems, right, which I will actually spend the second, I will hopefully have time to tell you a lot of stories about how developers will use machine learning in a wrong way. So that's the research that we have been doing in the last few years. So we try to think about, like I heard the word ecosystem, right? Yeah, we are trying to think about from the software that use machine learning to the system, OS and hardware setting, and then to machine learning algorithm design. We want all these vertical stack to work together to eventually get an application that end user are happy with. So I want to very briefly go through what we did at algorithm level, system level, and then hopefully I can tell you more stories about how developers, right, they use machine learning in a bad way. So from the algorithm level, right, I already told you, right, the particular challenge we were thinking about, how can I pick the model that fit my usage need? So the challenge is that, right, I can only, all those models, right, you can have many different models, many different architecture, but they only give me one particular time and accuracy trade-off, which I don't like. So we want to, our hope is that we can have one model, and this one model will combine all these trade-off points. Basically, I mean, people have proposed this idea before. This is called anytime inference, right? So that it will incrementally, with time goes on, I hope my model will incrementally give me more and more accurate result. Okay, so this way, no matter how the runtime environment changes, right? If the deadline is here, I will output. No matter how the environment changes, I always give you the best I can. Okay, so now how can we do that? So before we did this work, the best we can find is this cascade approach. So basically, just have early exit, and it will give you some result. But the problem is when you have an early exit, right? If you did not design your model just for this anytime, when you have an early exit, then the early exit result, either it will be very bad because it skipped all the later layers, right, of your network, or you have to do a lot of extra work along the early exit edge, right? And all those extra work, they're kind of wasted if turns out I don't need this early exit result. So we want to have designed some kind of nested architecture so that all those earlier computation, the computation used for producing earlier result can be fully reused to produce the later result. So this way I can get this flexibility, right, of any time without sacrifice to performance and accuracy. So here is just one example. So we made several designs. So this is one example that we did. We call the depth nesting. So it's like, imagine, so this is based on a sparse net. So imagine this would be the first output, and then the next output will follow this. Or if I kind of use another view, so this is what it's like. So you can see the first output result will be fully reused to produce a second result, and we kind of like just double the size, and the result will be more and more accurate. And then so we made a big family of design. So there's also a way of doing width nesting. So depth nesting has more requirement for the neural network architecture because it has to have the original network has to have this skip forwarding. And it has to be like power of 2 skip. Only that type of can be adapted to become depth nesting. For width nesting is much easier. And basically, taking a ResNet or whatever, a transformer model, what we need to do is we do need to cut some edges because basically we want to make sure that because we cannot use for later output, right? To do the later outputs computation, their result cannot be used for the early output. So I will skip all this. So basically that was, in collaboration with the machine learning people in our department, we have this anytime thing, and we feel like this will make the use of machine learning much easier. And there's also related training algorithm. So with this, right, so we believe this will make the runtime deployment easy. I don't need to make difficult choices. And then at the system level, right, so that anytime it doesn't solve all the problem. Because at the runtime, still there's a choice that, for example, if my runtime resource, right, resource contention is very stable, then we don't need any time, right? And then this goes back to the choice of, do I want to pick, do I want to, for example, I can set the power setting, right, so that the CPU frequency is very high. And then I can run more complicated algorithm, more complicated, bigger model, and then, but performance will also be good, but the energy consumption will be bad, right? I can also pick just a bigger model, but again, that hurt both performance and energy. So anyway, so it's like this is actually, if you think about it, it's a very big decision space because you have to consider not just the scheduling, right, and the hardware frequency, power cap setting. You also need to decide which neural network to use at the same time, and you're making these decision and adjustment when you are, for example, processing a streaming video. So all this has to be done. All this decision at system level has to be done with very quick speed, right? And you are adjusting not only the system resource but also neural network picking. So I will skip all the detail, but the high-level idea is at the end we have a system that uses control theory-based technique, and at runtime we'll make some neural network and system setting selection. And we keep our measurement to see how far away from the energy consumption go, okay? So by the way, so all this we're assuming you're deploying the neural network in your device, for example, in your phone and so on, right? So that's why the energy assumption potentially is very important. And then based on how far we were from the energy goal and accuracy goal, we will use control theory to make some adjustment. At the same time, we keep doing very efficient prediction. Predict that for different model at a different frequency setting, how much time it will take for it to finish. Okay, so basically that's just a very quick overview about what we have done at the algorithm level, system level. And then next, I want to tell you like my favorite topic, which is how programmers tend to make silly mistakes. And the setting in this setting is, so we have seen that, I know there are many machine learning experts here, but for people like me, right, who doesn't know that much about machine learning, something we really like is a lot of cloud providers, they're offering these machine learning APIs. They're very easy to use. I don't need to do any model design. I don't even need to run the inference on my computer. I can just run it on the cloud. So it's very easy to use. And if you look at GitHub, right, so then you can see that there's a huge increase, I would say almost exponential increase about number of open source applications you can find on GitHub that are using machine learning APIs. And the bar that we have for 2022, actually that's just a half year's number. So it's really a huge increase, right? Not a surprise. But, well, so in this case, right, we just talk about you need to pay attention to correctness, energy, and performance. And I will give you some example. You can see that the developers, they can really, a lot of times they really don't know which machine learning API to use. They don't know how to prepare the input. They don't know how to interpret the output. And once that happens, right, it's not even about trade-off. You can potentially damage you can have slow, energy consuming, and inaccurate result all at the same time. Okay, so we have done a series of work, actually more than these two, but basically today I just will quickly tell you, we did some empirical study, and just to get a sense about how widespread machine learning misuse exists. And we also developed some automatic static checkers to automatically find some of this machine learning API misuse. And then we also developed a testing framework to allow you to automatically test your software that use machine learning. Okay, so so we did this study because before that, we see there are a lot of studies looking at, for example, have you implemented machine learning library correctly? But there was no study about how people are using machine learning correctly. So we looked at GitHub, and we manually identified 360 applications that we believe are using machine learning in a non-trivial way. Basically, these are not homework. Okay, and most of these are Python applications. And they cover the machine learning APIs that are used by them cover 3 major domains, vision, speech, and language. And most of these applications are very, very new. So they're about 1.5 years old when we studied them. Okay, so this is a high-level result. Okay, what you can take back is 2/3 of the software that use machine learning are using them in a wrong way, one way or another, okay? And almost 40% of software, okay? Their software use machine learning in several places, and at least 2 of their uses are wrong. Okay, so this is a very scary result, right? And then let me just give you some example, right? How, right? What kind of mistake people are using. So a lot of times people don't know what machine learning API to call, right? There are actually not that many machine learning API, but sometimes there's subtle differences. Like every cloud provider offers image classification API and object detection API. Okay, a lot of people, they don't understand the difference between these two. Okay, I know this is another problem, right, for all the audience. But just to give you an example, there's an application that's called Smart Fridge. It does offer, smart fridge. How smart? Well, it says I will take a photo of inside your fridge, okay, and then I will automatically recommend some recipe to you. Okay, so before you open your fridge, okay, we will recommend what recipe you can use for your dinner. Okay, so now what vision API should you use? This application uses image classification. Okay, so if I do some simple testing, it totally works, right? I have this, and the image classification tell me their food, egg, and a box, and then it actually will recommend some legitimate recipe. Okay, now you probably already realize what's the problem here. Okay, so here is kind of like more like what you will see, right, in your fridge. And if I use image classification, okay, so this is a real result, okay, you will get from a Google image classification API. Okay, tell you the natural foods, local food, vegetable. Okay, I cannot generate any recipe, right, just based on their food. Okay, and you developers, right, or users, at this point, you may just think, wow, probably just machine learning. These days, machine learning techniques are not good enough, so I don't get a recipe. Okay, and you probably realize no, the problem is not machine learning's problem. Right, it's not about I need to have a bigger model. It's just because you need to use object detection. Right, if you use object detection, you can see, right, for this is a result from Google object detection API. It has perfect result, right? And it can generate a very legitimate recipe. And so we studied this, and we see that about in every 10 applications that use image classification, 1 of them is wrong. They should have used object detection, and the other way is also true. And there are other APIs that have subtle difference, like in Google offer text detection and document text detection, right? From the name, you cannot tell what's the difference. It turns out 1 of them is particularly good for manual written, handwritten. The other one is more for computer, right? And who can tell, who knows, right? What is this for? The next category is sometimes people don't know how to pre-process their input. So for any image, right, API, there's a question about what kind of resolution I should feed into the API. So here is we use Google Vision API to did some profiling. And it's not a surprise, right? So you can see when the resolution of the image goes up, the latency, right, definitely goes up. Okay, now what about accuracy? This is not something that Google's API tells you. So the accuracy actually saturates very early. At about 320 to 240, that's a very poor resolution. And at that point up, you don't get better accuracy. Okay, so if really, right, if developers knows this, right, then you would know that, because this is you send the image to the cloud, right, and you have a larger resolution, it really hurt. So actually, everybody should have, right, downsample your image and just submit a lower resolution, and then that you can see that will save your performance, that will improve your performance 3 or 4 times. Okay, so the last category, we call it how to interpret the output. Okay, so some output, like the image, like the object detection API, right? Tell me cucumber, egg, everybody knows what it means. But there are also APIs. For example, Google has a sentiment detection API. It output 2 floating point output. One is called score, and one is called magnitude. Okay, so the picture shows what I put here is the correct interpretation. So it's like, if you want to know whether it's a positive or negative sentiment, actually you have to consider both. Okay, and you can imagine a lot of developers don't get it. So there's some application that the input, it's a electronic diary. So for every diary entry, it will add a sentence based on the sentiments that it inferred. So if I have sentences like this, that software will say, sorry that you had a bad day, right? If you're using this application, you would feel like, what is going on, right? This software is not working. The reason is, for this sentence, the sentiment detection's output is at that dot, okay? So the score is a negative number, but the magnitude is kind of medium. So in this case, actually, it means a mixed sentiment, right, which is correct. But it's really difficult for non-expert to correctly interpret this floating point vector. And you can see 40% of people who use this API is using their result in a wrong way. Okay, so we manually, my students, manually went through this 360 application, and you can see there's hundreds of problems, and this is because of different reasons, and some of them affect accuracy, some of them affect performance, some of them affect cost, because Google, right, Microsoft, they charge you based on each API call. So there are many, many others. So we also built, for some of these can be automatically checked. And we built some automatic checker, right? And then we just crawl the GitHub, right? You can imagine we found thousands, tens of thousands of problems. So takeaway message, right, is it's really not easy to use machine learning API. And no matter how well the machine learning model is, right, if I use it wrong, it doesn't help. So we really need some tools to automatically detect. So I want to just very quickly go through. So we built some tools to do automatic testing. And it's not easy. So here is an example about a software. And I can tell this software has a problem, but it's hard to tell. So this label detection is Google's image classification API. For a given image, it will run this API, okay? And it will use the top 3 labels. It concatenated it into a string, and then it check whether fire is in this word fire is in this string or not. If it is, and it will trigger an alarm. Okay, so this is a smart fire alarm application. Now, how can I test this piece of software. It's very difficult. So there are several challenges. First of all, the input. How can I automatically generate input, right, to test this fire alarm? So it's challenging because this is not just about general like model training, right? This is about the real fire alarm application. So we'd better use some realistic input, right? And it's not just realistic. I want to use a relevant image, right? So if you just give me a bunch of dog images, right, this will not be able to test a fire alarm application well, right? So I hope that you can give me some images like this one, right? How can I automatically generate? And secondly, it's very difficult to automatically judge the output, right? As a human, I know this one, if you give me this image, this should be a fire alarm, okay? But how can I automatically tell? Okay, right? So these are the challenges in testing, okay? And I just give you a comparison, right? If you give me, say, a square root, right, a library, there are mathematical properties I can use to automatically judge the output correctness, right? But there's no such mathematical relation I can use here. Okay, so very quickly, what do we do? So there are a lot of compiler technique behind this. So I'll just tell you very high level. For testing, there is a compiler technique, mature technique called symbolic execution. So if there's no machine learning, okay, then what symbolic execution will do is it will mark the input alarm as symbolic. And then it will use symbolic execution, and it will realize that to have this program has two branches. And these are the conditions that it will generate to cover both conditions. And then it will actually, the symbolic section will generate concrete input to cover both branch, right? Very good. Okay, now, if I have machine learning model, this completely changes the story because symbolic execution cannot scale to billions of flops of computation. It cannot scale to millions of symbolic variables. This doesn't work. So what can we do? So our solution is I model the output of a machine learning API as symbolic. Okay? Then I run the traditional symbolic model. Then it will tell me, it will automatically tell me, hey, this API output needs to have fire and not have fire in order to cover all the control flow paths. Of course, this only solves half of the problem, right? Then how can I let the API to generate fire? So then we introduce a concept we call the pseudo-inverse function. What's this pseudo-inverse function? So what we did is very simple. If you tell me this needs to output fire, I just do an image search. Okay? And then this will give me the test input. And we emphasize this is not a mathematical inverse because, right, I did this through an image search. So the API may or may not generate a fire label, but this is just, right, what we expect. If you have this image, right, we expect those labels. And this is very helpful, okay, because it's not a mathematical inverse. So what do we actually get? And by the way, we have different ways to have this. There's synthesis-based, there's search-based. I skip the detail. Okay, so it's good because now I not only get input, right? I get those images. I get some floating point value. I also get what's the expected execution path, right? I just told you it's very difficult, right, to automatically judge the output. And now that problem is solved, right? Because when I did the image search, right, if I trust the image search result, and that gave me the expected execution output. And then I run this and see what's the actual execution path. Okay? So if there is the same, then we think the execution is correct. If they do not match, it's incorrect. And just very quickly, I can tell you, so if you feed these, okay, into the application, and then you will see that these two images actually do not trigger the alarm. The reason is for image like this one, the Google's image classification API will tell you this is a flame, It does not put fire in the top 3. It put flame in the top 3, right? Of course, so this is actually a good example that the machine learning's correctness itself does not represent whether the software is correct or not. So this also allows us to make suggestion to the developer, right? We would suggest that you may want to put a flame in your branch. Okay, so given the time limit, I will skip. I mean, we can find not just this kind of accuracy problem, we can find a bunch of other problems in our testing model. We can give you automatically very high coverage, like in our case, 90%, much higher than if you use fuzzing, and also higher if you just use a machine learning data set. So basically that's it. So this is just a brief overview about we believe there need to be a vertical approach to this problem. And there's still a lot of open problem. I think it needs an effort from compiler, software engineering, and machine learning people. Thank you.
Mic test? Great. So thank you very much, Professor Shan Lu. And we do have time to take a couple of questions from the audience. Yes, please.
Hi, great talk, thanks. So you were referring at the end in this testing part of the talk about the inability to, let's say, grok neural networks by a symbolic execution, right? But imagine that we had an ever so powerful machine and it could actually do that, right? Arguably, though, that would still not be necessarily the solution. And the reason I say that is that the space of all the inputs, right? Symbolic execution would not be able to tell you why certain pixels or inputs should really be marked as fires, whereas others would not, right? So there's something more, right, that is missing. I wanted to just probe whether you have a sense about how to better convey behavior, expected behavior for neural networks. There's been some work in formal methods and so on, but I don't think we're quite there yet. So I would like to pick your brain on this.
Yeah, that's a great question. So initially, we were thinking about symbolic execution. We were even thinking about whether to give it a try. And then later on, when we look back, kind of just like you were saying, even if I can run symbolic execution, I think that's actually not what we want, right? Because if I have symbolic execution, it will be like I will get a perfect inverse function, right? It will be like, given the symbolic execution, if I have symbolic execution on a neural network inference, then I can perfectly generate an image, right? That will guaranteed to produce fire, and some image that guaranteed to produce not a fire. And whether this image is a realistic photo or not, I have no idea, right? And also, if this one is guaranteed to produce fire, then what exactly I'm testing, right? So when we look back, we realize actually, right, not running symbolic execution, but rather use something like an image search, right, actually serve us much, much better. But I do think symbolic execution, if in the future, right, if we can run a symbolic execution on a neural network inference, it probably will help us to do other things, right? For example, maybe you can say, I want to see, right, what kind of image, for example, can cause this neuron to be triggered in a particular way, right? I think it probably will be able to help some of that.
Thank you for the great talk. This is Hussein from Beyond Limits. I'm more interested about the automated quality test for the machine learning models and the APIs. We're trying to use that within a framework, with a bigger framework for MLOps, when we monitor, for example, ML models or APIs in production. I'm wondering if there is any existing framework that they are planning to publish out of this work.
You mean if we?
Yeah, if you have any software or tool that's already published or are planning to publish out of this research.
Yeah, so actually our tools are all open sourced. So I would say, so right now So actually we have, let me see, did we? Yeah, so for example, we actually have, we not only have open source, and also we actually have a, for example, this is a IDE plugin. So I believe this is for VS Code. It's a very popular, you know, Python development IDE. So actually we have this plugin so that people who use the API can just, they can, this IDE plugin will automatically tag their problem. Our testing tool is also open sourced. I realized I didn't put a link on my webpage. I will add it, and if you want, we can chat about it offline. So right now, the limitation of our testing tool is it only tests, it's particularly useful when you use a machine learning result to make a control flow decision, okay? If you use machine learning, if you use a machine learning result, but you don't make it to make control flow, right? It's like, because our symbolic execution is particularly targeted, right, to cover the different branch. So if instead you just use, for example, numerical result for whatever computation, and we won't be able to test it well. So that's the current limitation.
All right, we are at time, but just to check, is there anybody who still has a question for our guest? So it looks like we'll do that.
Yeah, it's an interesting perspective. Do you hear me at all?
Yes.
Yeah. I'm kind of curious. You were showing this fire versus flames and things like that. So, like, from your perspective or from experience, to which degree the API that is exposed from the cloud providers is introducing a problem? So, like, I'm mostly asking about maintainability of the things. Like, you do this application design, you do fire, flames, and then, you know, they add, you know, something else, right? And your application stops working, things like that. So is this a common source of the problem, or you haven't looked at this? I'm just kind of curious from you're kind of becoming dependent on what cloud providers are making.
Exactly,
right?
That's right. That's a great question. I mean, I feel like it's a huge problem. And I can see this fire flame. There are many examples like this. So for example, another example is some people use maybe pants, and turns out there's no pants label. There's only trousers label. And I do feel like there's a maintenance issue, right? Because I can totally imagine one day they would say, oh, there's no trousers, there's only pants. I feel like to some extent it's an inevitable problem, because for when your machine learning model is very powerful, right, it will generate tens of thousands or millions of labels, right? And so as a result, I think what is missing is there need to be a tool, right, that help users to navigate, right, to know that what labels are available, right, potentially. So what we're doing is we actually do a kind of a knowledge graph search. So we suggest that you may want to add a flame. It's not just because flame is in an image that you didn't detect, right? But also we actually checked the knowledge graph, and we saw that flame is close to fire. So I feel like there need to be some kind of, you know, tools, right, at the middle layer between the machine learning model's output and the developer to help developer to use the complicated model. Thank you.
Okay, all right, great. With that, let's thank our speaker once more.